All right, last problem, and it's a toughie. So be patient. Don't try and understand everything all at once. You may have to watch a couple times or ask a couple questions, and that's totally okay. But in a made-up scenario here, in 1985 and 1987, the Oklahoma Department of Natural Resources placed 61 buffalo in the Black Mesa Preserve. I don't know if they really did that or not. But it was originally hoped that the population would reach a carrying capacity in 25 years with a growth rate of, or change in rate of, the population being this differential equation right here. Okay? And according to our model, we have some questions we can answer. Number one, according to our model, what is the carrying capacity? And in that case, the carrying capacity is always this number right here. So the Black Mesa Preserve will hold 1,000 meese, or mooses, or plural of moose. With a calculator, generate a slope field for this differential equation, so be able to do that. And then lastly, solve the differential equation with the initial condition that when t is 0, p is 61, and show it conforms to the slope field. So we want to solve this differential equation with this initial value right here, P0, and that's T. Population equals 61, that's P. So to do that, we're going to multiply both sides of our equation up here by dt, okay? And then divide by the P's the other way. And one thing that I'm going to do here that actually will make our life a little bit easier is I'm going to leave 0.003 on the right-hand side. Because in the long run, it'll make our problem a little bit easier. So I'm actually going to solve this integral right here. Divide by p, multiply by dt, and you end up with dp over p times 1,000 minus p, which is equal to the integral of 0.003 dt. And that came from right here. I'm going to divide by this part right here. Divide by that part, okay? Multiply by dt, and you get this for our integral. Now, we've got separation of variables right here. Separation of variables right here. So this is going to be 1 over p times 1,000 minus p equals a over that first p plus b over 1,000 minus p. Okay? And multiply the whole thing by p times 1,000 minus p, and you end up with 1 equals, ooh, that's really light. 1 equals a times 1,000 minus p plus b times p. All right, because everything cancels out. And so we're going to let p equal 1,000. We're going to let p equal 0 because we can pick the p. All right, that's our variable here. And so what I get then is if I let p equal 1,000 and p equals 0, that's what makes this work. So I get 1 equals, if I do 1,000 first, a times 0 plus b times 1,000. Okay, so b is going to be 1/1000th, and I'm just going to go ahead and write it as a decimal. 0.001b is equal to b. Okay, that's this part right here. Okay, then I do the same thing for a. So 1 equals a times 1,000 minus 0 plus b times 0. And so this is going to be 1,000 to a, so 1/1000th. And that's this guy. All right. That takes us to the next part of our problem, which is we're going to integrate 0.001 over p plus 0.001 over 1,000 minus p and if I integrate, I can go ahead and integrate the right-hand side. That's going to be 0.003t. One more zero in there. Okay. And when I integrate the left, the first guy integrates no problem whatsoever. That's just going to be 0.001 times the natural log of p. Now the next guy, look right here. You see that minus sign in there? This is a cool trick that we can use when we integrate natural logs. That 1,000 minus p means we're going to have minus, instead of plus, minus 0.001 times the natural log of 1,000 minus p. Okay? And that's going to equal 0.003 and then plus c. Okay? Now we're getting really close to the end here. We're on the home stretch. I'm going to divide everything. I don't like all these small decimals in front. So I'm going to divide both sides of the equation by those bad boys. And I'm going to work with, from here on in, this equation right here. Natural log of p minus natural log of 1,000 minus p equals 0.3t plus c. Okay? All right. We're going to pause right here for a second. I'm going to clean the problem up a little bit. I'm going to give us some more room to work. This is a long problem. I'm going to give us some more room to work, and then we'll finish it. Okay? So give me 1 second to clean that up, and then we'll get going on the rest. Okay. Whew, this is tough. What we're going to do now is follow a couple more steps here. The rest of this is algebra, and this algebra can be killer. But and again, this is maybe not something you're going to get right off the bat, but it'll make life really nice in the long run. And what we're going to do is multiply both sides by -1. Okay? We're going to multiply both sides of this equation by -1. That gives me then natural log of 1,000 minus p minus the natural log of p equals -0.3t. And remember, c is a constant, so he can stay that or not. It doesn't matter. But since we multiplied by a -1, instead of having the plus c, which is what we're used to, I'm just going to go ahead and put a -1 in there. So it would be -c. All right. And then we're going to combine these guys together using properties of logarithms. And remember, if you take one logarithm minus a second logarithm, then you divide the things inside. So this becomes the natural log of 1,000 minus p divided by p. And that's going to be equal to -0.3t minus c. All right. And then we want to get rid of the natural log. And so we're going to rewrite this in exponential form. So we're going to raise both sides. We're going to use e, raise both sides to the natural e to the whatever power. So on the left, I get 1,000 minus p divided by p equals e to the -0.3t minus c. All right? No problems there. What I can do now, again, this is more algebra. If I have 1,000 minus p over p, I can separate that into 1,000 over p minus P over P, which is 1. So I'm going to add 1 to both sides. All right, and then I'm going to remember also that I have this situation up here where I've got e to the negative 0.3t minus c. So that I can also say that as this. Still minus p. Whoops, not 10,000 minus p. That's a whoops. That guy's gone. Still 1,000 over p equals e to the negative 0.3 t times e to the negative c plus 1. And then once I get here, I can now substitute in my initial value for p and for t. So t is going to go to 0, p is going to go to 61. So I end up with 1,000 divided by 61 equals e to the negative 0.3 times 0. So anything to the 0 power is 1. So e to the negative c plus 1. All right. And then I'm going to get a decimal over here. So 1,000 divided by 61 minus 1. Again, algebra. The algebra is a killer on this problem. And so when I get done, over here on the left, I should get 15.393 equals e to the negative c. Okay, so everywhere I see e to the negative c, I can put in 15.393. All right? Well, that's back up here on this guy. So again, with the algebra, 1,000 over p is equal to 1 plus e to the negative 0.3t times e to the negative c, which is 15.393. All right. The last step on this, and we're almost done, is to actually solve this guy out for p, which means that p on the left and 1 plus all of this on the right, they just trade places. Okay? So the final answer on this, and it's a long one, and I feel your pain, is this right here. P equals 1,000 divided by 1 plus 15.393 e to the negative 0.3 t power. Wow, that's a long problem. That's a tough problem, and this is one that we're going to probably have to work in class once or twice. But it's also one that you need to, by sitting through and getting this, I know that there will be some confusion. Ask any questions that you have, tweet any questions that you have, and I can help you with that. All right, so there you go, logistic growth. And if you'll look, this matches a logistic model, and if you graph it on your slope field, it'll be a perfect fit. Okay?